So hello, my name is Alexandre Moine, and I'm going to present the result of the first year of my PhD under the supervision of Charguéraud and François Pottier about a high-level separation logic for heap space under garbage collection. So our goal is to formally verify heap space bounds using separation logic, since it's a very powerful tool to verify programs, and by viewing space as a resource. And by doing so, we follow a long line of work started by Hoffman in 1999, where he used one diamond here, or one space credit, to represent one free memory word. And without garbage collection, things are almost easy, because allocation consumes space, whereas dually, free produces space. So allocating a block B consumes the size of B space credits and produces a valid points-to assertion, and dually, freeing allocation consumes the points-to assertion and produces space credits. However, in the presence of garbage collection, we do not have free anymore, so there is no more syntactical point to recover space credits. And let me illustrate an example the subtleties of heap space bounds in presence of garbage collection. So this is a mapsec function. Mapsec takes a list of integers and produces a new list of integers containing the successors of the element of the first list. The definition is by induction over excess. If excess is nil, the function returns nil. Otherwise, if excess is made of a head y and a tail ys, the function first computes the successor of y, then calls itself recursively on the tail, and finally allocates a new list cell to store the result. And the big question for us is, in the presence of garbage collection, how much heap space does mapsec need? And the good answer is, it depends. It depends on the evaluation context. Indeed, if excess is unreachable from the evaluation context, then just after matching on excess here, excess, the front list cell of excess is now unreachable, so the GC can deallocate this list cell, and the allocator can reuse this space to allocate the new list cell. This little game can be played at each recursive step, so no new heap space is needed. However, if excess is reachable from the evaluation context, the GC cannot deallocate it, so heap space linear excess is needed. So at the core of the problem to verify these specifications is reachability. And prior work was made last year by Jean-Marie Madiot and François Pottier, where they used pointed by assertions to record predecessors. With this pointed by assertion, location L is pointed by the multiset of locations capital A. And crucially, they have a logical deallocation rule. This means that if L points to a valid block with n values, and if L is unreachable, and unreachable is from the root, and unreachable from the heap, then this is a purely ghost operation, purely logical operation. By giving up these two assertions, the user gets back n space credits, the space of the now unreachable block, and dagger L, a proof of unreachability of L. But they target an assembly-like language where roots are explicit, so the user manipulates stack-to-heap pointers, which leads to non-standard syntax and semantics and very polluted reasoning rules. Whoa. What is going? Okay, very polluted reasoning rules. These are the rules for load and store, and you can see the locations between brackets that denote explicit roots. So what are the challenges to target a high-level language? The first challenge is that roots are implicit. In high-level languages, we do not manipulate stack-to-heap pointers. So we need a logical deallocation rule of the following form. We can reuse the pointed by assertions to track heap predecessors, but we need something more to track roots. The second challenge is closures. Because closures are heap-allocated blocks that points to the values of their environment, so they introduce implicit heap-to-heap pointers. And then the contributions of this work is the first logic to reason about a heap space consumption for heap space consumption in a high-level ML-like language with closure. So we address these two challenges, and I will first focus on how we reason about roots in a garbage-collected lambda-calculus, and then going back to reasoning about closures and the heap path they introduce. So the first question is, what are the roots considered by real-life garbage collector? And thankfully, we have an answer provided by Felison and Hib, that is the free variable rule. It says that in a substitution-based semantics, the roots are the locations occurring in the term that remains to be evaluated. It is a complex definition, so let me illustrate it on an example. Here is a simple term, let A equals ref4, ref2 in bang A plus bang B. And we start in the empty heap. So first we allocate ref4 to a location LA that points to 4. Then we substitute A by its value. And notice here that LA occurs in the term that remains to be evaluated. So LA is the root, hence it is reachable. Then we allocate ref of 2. We substitute B by its value. We dereference LA. And now notice that LA does not occur anymore in the term that remains to be evaluated. So triggering garbage collection here can deallocate LA. And so on. So the free variable rule is about the whole program. And we like to reason locally on subterms. So while reasoning on the subterm of a program, roots may occur either in the subterm under focus, and we call them visible roots, either in the evaluation context, and we call them invisible roots. We cannot see them. So to formally prove that a location is not a root, to deallocate it, the user must prove that it is not a visible root and not an invisible root. To prove that the location is not a visible root, this is almost easy, just inspect the term under focus. To prove that the location is not an invisible root, we need something more, because we cannot just inspect the evaluation context, and we introduce a new separation logic assertion to track invisible roots. So let me introduce this assertion. This is a stackable assertion with a location L and a fraction P between 0 and 1. And the main property of the stackable assertion is that the full stackable assertion with fraction 1 asserts that L is not an invisible root. And with this almost magical assertion at hand, can unveil our logical deallocation rule. That is, if L points to a valid block with n values, if L is unreachable from the heap, if L is not a visible root, this is almost a syntactical check, and if L is not an invisible root, thanks to our stackable assertion, then by giving up all of this, the user gets back n space credits and the proof of unreachability of L. But don't worry, there is no magic at play here. Let me illustrate how the stackable assertion works. So first of all, the stackable assertion is fractional. This is a standard notion in separation logic. If we have stackable of L with P plus Q, we can split it in two stackable assertions. And the key technical idea of this talk is that we are going to withhold stackable assertions of invisible roots. Let me illustrate this. This is a simplified let rule, so we are focusing on the let x equal t1 in t2 under precondition phi, and this is the standard separation logic rule. And there is only one location in t2, L. So while reasoning about t1, L will become an invisible root. So, as I said, we are going to withhold a stackable assertion while reasoning about t1. So we force frame somehow this assertion. And the idea here is that as we removed a part of the stackable assertion from the precondition, the full stackable assertion cannot occur in the precondition. Hence, no logical deallocation is possible of L while reasoning about T1. Okay, so I'm reaching the middle of this talk. What is left? I'm going to present the other reasoning rules of these systems and going back to the example of MapSec. Then, of course, the Soundness Theorem of this logic, and concluding on closures. So, pointed by and stackable assertions are created upon allocation. So, allocating a block n consumes n space credits and produces a fresh location L, pointing to a valid block with n unit values. L is fresh, so L is not pointed by anyone in the heap. And L is fresh, so L cannot occur in the evaluation context, so we generate a stackable assertion. Then, this is maybe the most difficult rule of this system, that is store, because store modifies heap predecessors. So here we have a location L pointing to a block W, and after offset I of W, we have the value V that we are going to override with V prime. So L will become a predecessor of V from the heap, But L will not be anymore a predecessor of V prime, but L will not be anymore a predecessor of V. So we require in the precondition a pointed by assertion of V prime that we are going to update with L to notice that L is no predecessor of V prime, and we generate a new assertion to remove L from the predecessors of V. And the fraction 0 and negative multiset may surprise separation logic experts. This is the proof pearl of our paper. So I'm almost ready to unveil our specifications for MapSuck. First of all, pointed by stackation and stackable assertions often go together. So we introduce what we call a handle here, this hooked arrow that is just a conjunction of a pointed by assertion and a stackable assertion. Then, recall our two specifications for MapSuck. If the argument is unreachable, we do not need space. It is exactly this specification. So this is MapSuck of XS. If XS is a list of model capital L, and if XS is unreachable from the heap and from the evaluation context, then we do not need any space credits. And MapSuck will consume these two assertions and produce a fresh location ys pointing to a list of the correct model, and ys is unreachable from the heap and the evaluation context. Now, the second specification, if the argument may be reachable, we still require that XS is a valid list of the correct model, and we now require space credits to allocate the new list. Notice in the precondition that MapSuck returns a correct list, a list of the correct model, ys is fresh, and the user still gets that XS is a valid list. So the user can continue to use XS as it may appear in the evaluation context. Okay, but now take a step back. What are we proving is this logic? Of course, you are all waiting for it, the Soundness Theorem. Our semantics is parameterized by a maximal heap size, capital S, and it interleaves reduction steps and GC steps. Crucially, an allocation is stuck if, after a full GC, there is not enough free space. And the Soundness theorem of this logic asserts that if we're able to verify a program T under the precondition of capital S space credits, then T cannot reach a stack configuration. We can reformulate this theorem by saying that the live heap space of any execution of T cannot exceed the maximal heap size. Okay, great. So now the second contribution of this paper, handling closures. So what are closures? Functions with an environment with free variables are usually compiled down to closures. And a closure is a heap-allocated block pointing to the values of its environment. This means that in our logic, closure allocation will consume space credits for the allocation and will update pointed by assertions as a closure block points to the value of its environment. To formally specify and verify closures, we choose to encode closures as derived construction using closure conversion. This means that closure creation and call are not in the syntax, but we provide macros implementing them and provide reasoning rules about those macros. This means that we also verify the correctness of closure conversion. I will not show you the reasoning rules of closures, but let me illustrate the space interest of closure. This is a simple closure that is a counter. mk-counter is a function that allocates a reference r, porting to 0, and then allocates a closure that will increment r and get the current value of r. We can simply specify this closure using a counter predicate. This counter predicate is parameterized by f, the location of the closure, and n, the current value of the counter. Then doing a closure call on f will increment the value of the counter and return the current value. Then we can, of course, allocate this counter. So mk-counter will require space credits to allocate the reference and the closure, and produce a counter f initialized to 0, and f is not pointed by the heap and the evaluation context. Next, we can also deallocate the counter if f is unreachable is not a visible root, is unreachable from the heap, the evaluation context, and f from a valid counter, then we can deallocate it and get back the credits of the reference and the closure. And let me show you how we define this counter predicate pretty easily. So we introduce spec assertion to specify the closures. So this assertion is parameterized by the environment of the closures and pointed by the values pointed by the closure, then the specification of the closure and the closure location. Then to define the counter predicate, we just say that there exists a reference R pointing to the current value of the counter. R does not occur in the evaluation context, and F satisfies a specification, and R is fully pointed by the closure block F. Notice here that the specification predicate abstracts away the closure code. We do not reveal how the closure is implemented, only its behavior. Okay, but the counters, this counter example is pretty easy. The general case is challenging, as the closure may call itself recursively. This means that the closure's ownership must be transferred from the caller to the callee. And this is more tricky, but the closure specifications depend on itself, because we need to access the specification to prove the specification. So we have to solve a pretty tricky interdependency here. And perhaps this is more interesting from the point of view of space. A closure may become unreachable as soon as it is called, and somehow self-destruct. So we can reuse this space to allocate new things. And this is crucial, actually, for the space complexity of CPS-style functions when you allocate a stack of closures. So, sadly, I do not have the time to cover everything, but read the paper for details. I'll present a general case of closures, then simplified handling of stackable assertions. So in several cases, we do not require the framing of stackable assertions and their tracking. We also present several case studies, so CPL-style functions with list append, an amortized analysis with rational space credits to specify a list of chunks, verify a list of chunks. Then we illustrate the modularity of our specifications using stacks, and we implement stack of stacks. We also present the two fun technical contributions that are fraction 0 and sign multiset that may be of use for your next project. So read the paper for details. In conclusion, I just presented the first logic to reason about heap space consumption in a high-level language with closures, equipped with a garbage collector that obeys the free variable rule. Moreover, as my switcher said, the theoretical examples are fully mechanized in Coq on top of Iris. As future work, we are currently targeting concurrency and specifically verifying spacebound or lock-free data structures that are pretty tricky in presence of garbage collection. So if you are interested, come talk to me. We also like to verify and specify weak pointers and ephemerons. And we would also like to link this logic with the formal cost semantics that was developed some years ago for a Cake ML verified compiler. Thank you for your attention.
Yeah, thank you, Alexandre, for the talk. We have plenty of space for questions. So, Neil, by the way, please mention your name and institute before.
Hello, I'm Neil Krishnaswamy from the University of Cambridge. Could I ask you a question about the distinction between visible and invisible pointers? If you have an expression, say T1 plus T2, the visible pointers are things in the union of T1 and T2. But when you're doing the proof, if you start verifying T1, do you have to change the pointers in T2 from visible to invisible?
Yes, but this is implicit in the logic.
Okay, thank you.
Varun?
Vadim Zaleo from the University of Cambridge also. I'm a little unclear about the stackable. It looked like a predicate because it's 0, so 0 and 1. For example, how stackable L0 different from lack of stackable assertion?
You cannot have stackable L0. Fractions, I guess, it's 0 excluded.
Okay. So it's not, what's the values are? 1 or anything else?
Sorry?
Anything except 0?
Yes, any fraction between 0 and 1 excluded 0.
Oh, okay. Sorry, I misunderstood.
I saw.
I now realize I misunderstood something due to your answer to your other question, so I might have to retract my question. But I thought stackable LK was sort of like a ref count in some sense.
A ref count from the heap, yes. Maybe an inverse ref count, we're manipulating fractions, but yes, something like this.
Okay, I see, okay.
Okay, we are still pretty well on time, so if there are more questions, or I don't see them. Ah, great, here. Let's take one from the back there, please.
I was going to humiliate myself and ask whether, if you had an explicit stack model, you wouldn't need the stackable assertions. You could just use your pointed by.
Yeah.
And you're going to say yes. And if you'd bothered to read my paper last year, you'd see that's exactly what we did.
Yeah.
So I'm kind of relieved that I looked at it. I guess the other question, given that you seem to have discovered co-separation logic, is can you see other applications for that?
Oh. No, I don't know. Yes, I don't know.
I don't have enough category theory to know, but wherever there is a logic, there must be a co-logic. And if you've turned the pointers around, it seems that's probably what you've got. I think there are probably other things where that
Yes,
would work.
we can discuss this.
Yeah, I'd like to.
By the way, please continue the tradition of naming yourself before you speak, before you give your question. Ask your question.
James Noble, currently from nowhere.
Okay, great, thank you. So in the front here, there is another one.
So I'm Thibaut Parami from the University of Cambridge. And my question is that in the slide at multiple points, you express what is to be an internal root by referring to some term T that doesn't appear anywhere else in the rule.
Yes.
And that confused me a bit.
Of course.
Which T you are talking about?
Yes, of course, we have a new ghost update parameterized by the visible root that you can only apply on these triples. And then the free rule. So yes, it was a white lie.
Okay, so it's the ghost update under around
they are parameterized.
certain term. Okay.
Thank you.
Okay, we have time for one more quick question. Any taker? Okay, so let me ask you one. So you have mechanized all of this in Coq and Iris. So how easy or difficult is it to do proofs about concrete programs using your logic in Coq and Iris?
Okay,
with this logic?
It's still pretty hard to do proof, but we are using a diaphragm, a tool to do some automatic proof. So we hope that we can automatize many things. Like the handling of stackable assertions is pretty mechanic. So I hope we can automatize this.
Okay, that sounds exciting. Let's talk about that later. Okay, let's thank Alexandre once more.